Stream start. Good morning, everybody. No, not morning. Good afternoon, everybody. There's people here. That means you can respond. I say good afternoon. You say, oh, that's one. This is awesome. I don't know if you feel better being in person, but I feel so much better having an actual class of people to talk to. Okay. The camera. I love you, camera, but you're just not the same. Okay. All right. We're doing awesome stuff this whole next set of weeks, okay? I've specifically looked into, we've got problems to solve, okay? We've got area this week, then we got to move into surface area and volume, and like 3D shapes. I've made sure it's not just problem solving, okay? It's not just be problem set after problem set. We're going to have at least something cool to do every week, okay? Promise. And you guys here being in person, you get the hands-on cool stuff. Folks at home, I'm sorry, you're just going to have to miss out or find a way to do it yourself. You'll have a lesser experience. That's totally unavoidable. But I'm not going to like let you guys, your experience, be diminished just for their sake, okay? We're going to have fun. Now, today, we got to deal with some basics, okay? Before we can do the really fun, interesting bits, we got to master the basics so that when we get to the interesting bits, we can just run on autopilot and be like, oh yeah, that's parallelogram. I know how to find the area of that. Right? That's not the problem bit. The problem bit comes in finding, well, how is this arranged? Where is the parallelogram? What are its measurements? Right? Figuring that part out. And then the computation bit, oh, that's easy. We practiced that, right? So this section, which you read over break, and you got amazing notes, right? Color code and everything. Wonderful. No, if you didn't, you should go back and do that. Okay? You came up with 4 new area formulas. New-ish. They're not that different, right? Here we go. 4 shapes to deal with. We started with rectangles and triangles. Rectangles and triangles are a pretty good basis. You can turn just about anything into triangles. So that's going to cover a lot. But it'd be nice if we had some shortcuts, right? There's a lot of other shapes we encounter all the time. Let's put them together, see if we can make something besides rectangles and triangles out of them. And those are parallelogram, trapezoids, regular polygons of all numbers of sides, and then an infinite number of sides in the circle, okay? Really cool derivation there in the text of how you get the formula for circle from the regular polygon. Great stuff. You can read more about that there. So we're going to practice one of each together here in class, and then any leftover time you can just get started on the problem set, okay? And spoilers, the problem set has some really cool stuff at the end. Level 3 is very interesting, but I made sure to put, even in level 1, this wonderful application problem. How to get the best deal on pizza, right? We're all frugal here. We want to save as much money as possible, but we also want as much pizza as possible, right? So this problem will walk you through figuring that out. Which size pizza is the best deal for you? Okay? And you can use that and apply it next time you order Domino's. Okay? But before we get there, let's look at this parallelogram. And I haven't annotated the diagram up with the congruent sides, but I'm telling you it is a parallelogram, so you can trust opposite sides are parallel and congruent. And I have several measurements here. What am I going to use to find the area of this parallelogram? Do I need all 3 of them? No, 3 seems too many. If you recall from the rectangle and the triangle, you only need 2 measurements, right? The triangle formula added that extra 1/2, but that's not a measurement, that's a constant. So we only need 2 measurements. The question is, which 2? Or does it matter? Can we pick any 2? It doesn't matter? You can pick any 2 of these numbers and you'll always get this. Do you get the same result though? I don't think you have to run the multiplication to realize 2 times 1.8 is different than 2 times 2.5, right? So I think it will make a difference because we'll get different results. Only one of them can be the correct area of the parallelogram. So which 2 do we pick? Any ideas? Anyone want to make a guess? Where should we start? Angel, you got some favorites? 2 and 2.5? This one and this one. Those are both sides of the parallelogram. So it sounds like they go together, right? Two different sides. We know that these sides, match up to their opposites, so we'll get one of each. We'll have the full measurement. That's what we did with rectangles, right? We put one of each side, the base times the height. Well, the problem is these are not quite rectangles. They're slanted, right? This 2 meters does not actually represent the true height of the parallelogram. It's going a roundabout way, right? Imagine this was a physical thing. Here's the ground, and this stands up above the ground, and you walked this up. Are you actually 2 meters? Is your elevation changed by 2 meters? No, your GPS tracker would not tell you you've gone 2 meters higher. You walked that way, but that's because you took the long way. You went up the ramp. If you got in the elevator and went straight up, you'd only go 1.8, right? Because that's the true height. Notice what we've got down here. What kind of angle is this indicating? Say again? A right angle. That means those two line segments are perpendicular to each other. Anytime you calculate area, you need 2 perpendicular measurements. Except for circles. I forgot to mention that 4th period. Circles are the exception. We'll get to that later. Right. So, 2 measurements multiplied together, but they have to come from perpendicular things. If those 2 measurements are not perpendicular, they will not give you an accurate area. So that's your hint. That works for all of these shapes as we go forward. Find the 2 things that are perpendicular, multiply those. You're pretty much set. Because this is a true height. If you want to know the actual height from something, you need to measure straight up from the ground, right? We wouldn't measure the building by going, at an angle. It's about that tall. No. You want building straight up, right? How tall is it now? Straight up and down. So make sure your height is perpendicular to your base. Okay? So our area is base times height. So we can use that same formula, the same shortcut as the rectangle. The only catch here is that our height is not one of the sides of the parallelogram. This is just like when we dealt with obtuse triangles. Right? We can make it even more extreme, right? If we call this the base, we can't multiply by this other leg there. No. That's why we had to do this thing. We had to draw in that perpendicular height of the triangle. Remember that for the obtuse ones? Same thing with the parallelogram. You gotta have something perpendicular. The height is always perpendicular to the base. So in this case, we need to multiply 1.8 times 2.5. What do we get? She says 4.5. Does anybody agree? Yes, we got confirmation, 4.5. Okay, what are the units? Meters were the units of length there, so the area should be in meters squared. We multiplied meter times meter. Meter squared. Okay. Questions on parallelograms? Good. I want parallelograms to be easy. If you get a sheet of find the area of these parallelograms, you should be like, oh boy, this is easy sauce. I've got this. Right? The challenge comes in the other problems where they hide it from you. Right? They describe something and you first have to figure out, oh, I think they're talking about a parallelogram here. Oh, now I can deal with the parallelogram, right? That's where the draw a picture comes in handy. You draw out what it is, and then you look at it and realize, oh, that's a parallelogram. I can take care of it. Right? Once you get to there, you're golden. All right, second shape, the trapezoid. Trapezoid's going to be a little trickier. Once again, I have 3 numbers. Well, Mr. Apple said you always multiply by things that are perpendicular. So This 9 here, there's a right angle, is perpendicular to the 23. So the area is 9 times 23, right? No, think about if this was a rectangle. Look what would happen. Right? 9 times 23 would give you that rectangle, wouldn't it? That's too much. That's too big. That's no good. Hang on. You have the answer, don't you? I want to get there. I want everybody to see where this comes from. All right? Because the beauty of the trapezoid formula, for me, is how you arrive at it. 9 times 23 was too big. All right, Mr. Apple. I know all about trapezoids. I know that the two bases are parallel to each other, which means if this line is perpendicular to one, it must be perpendicular to the other. So this can also be a perpendicular measurement. 9 times 15, how about that? Well, that would give you this rectangle, wouldn't it? That's too small, right? One's too big, the other's too small. What are we going to do? We need the Goldilocks in the middle, right? What do we do if we have a number that's too big, a number that's too small? How can we find the Goldilocks in the middle? What would you do? Add them and then do what? Divide by 2. What do we call that? Is there like some name, some word that starts with A that could just describe when you add stuff up and divide by how many? Anybody know one? We could really use a word for that. That'd be a handy shortcut. Average, thank you. You're doing all the heavy lifting here. Average. Yeah, if you take the average of the two bases, because one's too big and one's too small, just average them. So we are literally going to take 15 plus 23 and divide by 2. Right? So we'll get the average base length. That would give us a rectangle that's in the middle somewhere. Multiply that base, this new average base, times the height of 9 will give us, well, as we've described it, it sounds like it gives us a rectangle that's about, that big, right? But that rectangle will have the same area as our trapezoid. That's the cool bit. So I've seen area of a trapezoid written as 1/2 times height times base 1 plus base 2. I don't like it written that way. I like it like this. Put the two bases over top of the 2 like that. Add them up, divide by 2. So you understand where it comes from. It is representing average of the bases times height. Okay? Trapezoids are the weird ones out. They've got 2 different sizes of base. So take the average base. Multiply that by the perpendicular height. There's your area. All right, what does that equal to? 171? Anybody agree? 15 plus 23 is 38. 38 divided by 2 is 19. 19 times 9? 171? Agree? And Leo, what are the units on here? What units do I need here? Centimeters. Just centimeters? An area. To the power 2. Centimeters squared. 171 centimeters squared. Okay. Any questions on trapezoids? And I've left my video on. Full video here. Let's get to that one. There we go. Now we can see the full screen on video. All right, next we have the regular polygon. All right? So if I tell you it's regular, you can already safely conclude that all the sides are congruent, all the angles are congruent. Now I just need to find the area. And this one is probably my favorite. Trapezoid was cool and all, but I like the regular polygon formula. Because the trick to finding the area of a polygon is actually not to find the area of a polygon, it's find the area of a triangle. Several triangles. We're going to slice this guy up like a pie, right? Or a pizza, if you prefer, right? Into triangles. You can slice anything up into triangles, it seems. Handy tool. You should probably almost add that to your list of problem-solving strategies. Well, did you try breaking it into triangles yet? Okay. And now, since all sides are equal, this side is 18, that means this side is also 18. And now look, they gave us this thing here, from the center to the perpendicular to the side. That length was 15. But now it's the height of my triangle. You see that? So now I'm just finding the area of a triangle. Except this triangle is the same as this triangle, is the same as this triangle, is the same as this triangle. They're all the same. So I just add all my triangles, or no, adding is too slow. We just multiply by the number of triangles we got, right? My area of my, in this case, pentagon is going to be 5 times the area of the triangle. And the area of the triangle, as always, 1/2 base times height. The base comes from one of the sides given. That's 18. And the height they gave us there, make sure that's perpendicular. If it's not perpendicular, it's not a height. And then we put that in. So my full area, this is still of the triangle, so the full pentagon here, it's 5 times 1/2 times 18 times 15. I like putting them all together. Yes, you could stop here. You could calculate this as is, then multiply by 5. Right? It gets you the same answer. I try to combine things into as big of an equation as I can and save the computation for the very end, because sometimes things simplify. Like right here, I would not type this into my calculator as is. I would notice, hey, 18 is an even number. 18 divides by 2 even gives me 9. That one's easy enough to do in my head, so why not simplify it? Save yourself a few button presses. Then if you still go to the calculator, now you only have to do 5 times 9 times 15. Right? It saves you a few steps. All right, 5 times 9 times 15, what do we get? 675. Jose Luis, what are the units? Inches squared. Very good. That's not too bad, right? Regular now, if it's an irregular polygon, you're going to have more difficulty, right? Clearly, there's no easy formula for an irregular. That's why it's irregular. But as long as it's regular here, all the sides are the same, turn it into triangles. That's what I do. Now, the book introduced a shortcut formula. The book said, hey, since you're doing the side length of the polygon anyways, and you're going to multiply that by 5 all the way around, isn't that just the perimeter? Yeah. And isn't this height? Here they gave a special name for that height of the triangle. The height of our triangle was the apothem of our polygon. And so the book introduced this area formula. You could find the area as the apothem times the perimeter divided by 2. That works. It can be a convenient shortcut if that works for you. I personally don't ever use that. I just always think of it in terms of triangles, kind of that way. Because very often I'll have to calculate the perimeter anyways. They usually don't give that to you. They give you a side length. I'm like, well, if I just got to multiply it up myself anyways, what's the point? It makes no difference which one you use. You're multiplying the same numbers together. Okay. Any questions on regular polygons? Okay. There's a couple in your problem set, right? This is a pentagon, so it's times 5. There's I think there's an octagon in there. So you'll break it into 8 triangles, and right. All right, last one. Final shape. The polygon with an infinite number of sides, the circle. Okay. And again, the text walked through kind of how you could derive the formula for the area of the circle from the polygon, assuming you just add more sides, more sides, more sides. But we're just going to go straight there. What is the area formula for a circle? Pi times radius squared. Pi r square. No, they're not pi or round. Real pie that you eat, right? You ever bought a square pie before? No, that'd be weird, right? Okay. Pi r square. Except, in this example, I thought one circle was too simple for you. So instead we have a circle inside a circle. I don't want the area of a circle. I want the area of the donut shape in between the circles. Okay? This is a very common question. Find the area in between two things. And it should be relatively intuitive. I think we can see that the area between will involve, what's that? Well, we're going to need the area of the big one, and we're going to need the area of the little one, and then you're going to do what to those two areas? What do you think? If I found the whole circle, that'd be too much, right? I don't want this. So we're going to subtract that. So maybe add this to your notes. Area of the big minus area of the small. Right? Just as a general note, because you'll see this type of situation come up a lot. Find the area between these two boundaries. You take the big one and you subtract off the small one. Right? Just like we could add areas together, we can also subtract off areas that we don't want. So we'll be using this quite a lot. So in this case, our areas are both circles. So the area of our donut is going to be the area of the 10-foot circle minus the area of the 3-foot circle. Would you agree? Big one minus small. Okay. So now let's fill in the actual formula for each circle and put in its appropriate radius. So we'll get first pi times 10 squared minus pi times 3 squared. Now, like in the preceding problem, you could have done these independently. You could find the area of the one, done, get a number, get the area of the other, done, get a number, then subtract those final results. But that's like the elementary school way to do it, okay? We want to do one better. We want to take advantage of our algebra skills and combine it into one equation whenever possible. Okay? Treat it as one big equation. I know it looks a little more intimidating, but the sooner you can get used to dealing with one big equation, you'll treat it in multiple parts, but have it all written there together. Because sometimes you'll find shortcuts, things to make things easier, or you'll find ways to improve accuracy, particularly when pi is involved. Because we don't have a perfect number for pi. We have an approximation, right? 3.14159. It doesn't matter how many decimals you use, it's never perfect. So we want to push the pi button on the calculator as few times as possible. Right now, if you type that in as is, you will have to press the pi button twice. But we could instead factor out the pi, right? Because this is two terms subtracted. There's a pi in each term. If I factor out pi times 10 squared minus 3 squared, right? Now I only have to press the pi button once. Now my answer is going to be a little bit more accurate because I don't have to rely on these rounded answers and then subtract those and lose off accuracy when I do the subtraction. I'll have the one approximation of pi. It's a little bit better. Yeah. Okay, everybody, 10 squared is? Is that everybody? I only heard one voice. 10 squared is? 100. 3 squared is? 9. Sounded more of a groan than a 9, but okay. 100 minus 9 is? 91. So my truest, most correctest answer is 91 pi. Ooh, what were the units here? The units are apostrophes. Anyone know what that means? Nope. Feet. So 1 tick mark means feet. 2 tick marks means inches. Okay. Handy shortcut, right? For Americans that use inches and feet everywhere and get, it's mostly the engineers that got sick and tired of writing it every time. They found even more, they like shortcuts even more than mathematicians. Okay? So 91 pi, back to blue, feet squared is our most precise answer. But that doesn't really register in my brain. You tell me 91 pi, I'm like, I don't, how much is that? If you go to the carpet guy, say, hey, I want a donut-shaped carpet. I'm going to need 91 pi square feet of it. They're going to laugh you out of Home Depot, okay? So we need a decimal approximation. Let's go 2 decimal places. So what is that? 91 times pi on the calculator, please. Is about what? What? 285. 0.83. Say one more time. 8. I did write 8. What? 8? 2 8s. Not 2 then 8. 8 and another 8. Okay, because 7, 8, 9. All right, I need to get my ears checked. There we go. Actually, you know what? Let's put a box around both of them. I like including both when in doubt, right? Just do both of them. You got the exact answer. Here's the mathematically most precise answer. It's beautiful. It's simple. If you need to do other things to it, further computations, keep it as exact as possible. And then your final answer, okay, but how much does that really mean? Then you get your decimal approximation. Okay. Questions on circles or donuts? All right. Then you have the rest of the period to work. I'll come around and answer any questions you have. Okay. Start on the problem set.